All right, so ocean atmosphere circulation changes. Ocean currents are constantly shifting in many different ways. Because of the ocean's important role in moving heat around the planet, these shifting ocean currents are responsible for much of the regional climate variations that occur over the time scale of decades. Sometimes these variations repeat with enough regularity that they are given names. The most important of these is the El Nino Southern Oscillation ENSO. During average times, there is a steady westward current along the equatorial regions of the Pacific Ocean that brings warm water to the western Pacific. However, this current is altered during El Nino and La Nina phases. The results are changes in global atmospheric currents and the distribution of heat around the planet. Oops. So over here, it shows an El Nino. So for the El Nino, during an El Nino, warm waters in the western Pacific start flowing towards the east. The polar atmospheric jet stream carries warm and dry air to central North America. The Pacific jet stream is strong and brings cooler air and lots of rain to southern North America. Okay, so again, this is an image right here of what's going on during an El Nino. Okay, so this right here is a low pressure zone. You've got the Pacific jet stream indicated by the red arrow. Okay, this area right here is wet. This area is right here cool. Over here, you've got a dry region. And then the blue arrow indicates the polar jet stream. Okay. And then the second image shows you what's going on during a La Nina. So for a La Nina, during a La Nina, the warm westward equatorial ocean current gets stronger, bringing more warm water to the West Pacific. A high pressure zone in the North Pacific brings cold air with frequent rains to central North America and warmer, drier air to the south. Okay, so again, this dark blue arrow along here shows the polar jet stream. The dark red arrow shows the Pacific jet stream. This area right here is a high pressure zone. This right here is a wet zone. Okay, this area along here is a dry zone. You've got a warm region right along here, and then a wet region right along here. And then again, this area right here is pretty cold. Okay, so suppose that you are a farmer living in Texas. Would you prefer an El Nino or La Nina phase of Pacific Ocean oscillation? Use the maps to construct an explanation to support your response. So what did you guys say? Do you remember what did you guys say for this question? Anyone? Okay, so first of all, with respect to the question, you know, does Texas include Central North America? Anybody? So yes, it does. So just for clarification purposes, okay, when it says Central North America, okay, and then in the question, they ask specifically about Texas or a farmer in Texas, Texas is in central North America, okay? So a farmer residing in Texas will prefer a La Nina phase of Pacific Ocean oscillation because a high pressure zone in the North Pacific brings cold air with frequent rains to Texas. Okay. So now let's look at variations in solar output. Shorter term fluctuations, the amount of light Earth receives from the sun fluctuates over the time scale of decades to centuries, affecting global temperatures. The sun's magnetic field flips polarity approximately every 11 years. The full cycle lasts about 22 years, and the total amount of radiation Earth receives varies by about 0.25 W over m squared over this cycle. The number of sunspots also varies over an 11-year cycle, correlated with the air radiance. This is useful because we have records of the number of sunspots going back to 1610 when Galileo first started using telescopes to observe the sun. This extends our record of the solar cycle back 400 years. All right, so again, we've got sunspots here, okay? And the sunspots are not physical objects, but slightly cooler regions of the sun's photosphere. The arcing solar prominences leave and return to the sun at the locations of the sunspots. When the sun's surface is hotter and energetic, there are more prominences and sunspots. All right, so over here we're looking at solar irradiance. The y-axis shows solar irradiance. The x-axis shows the years. Okay, the blue solid line represents the 31-day running mean. The dotted red line indicates the 365-day running mean. Okay, so solar radiance. Due to the reversals of the sun's magnetic field, the amount of sunlight reaching Earth's orbit fluctuates by about 1 W over m squared, approximately between 1360.7 and 1361.7 W over m squared. However, because this sunlight gets distributed across the sphere of Earth's surface, averaging about 340 W over m squared at any point on Earth's surface, the climate forcing from these sunlight fluctuations is about 0.25 W over m squared. All right, so now we're looking at the longer term fluctuations. The amount of sunlight Earth receives also fluctuates over centuries. A useful proxy for this is the record of carbon-14 production in the atmosphere. Okay, so carbon-14 decays over time, but it is replenished when cosmic rays from distant supernova interact with nitrogen-14 in the air. When the sun is more active, its stronger solar wind interferes with the cosmic rays, slowing carbon-14 production. The carbon-14 record for the past 1,000 years shows several pronounced dips that correspond to 4 distinct episodes of cold temperatures during the Little Ice Age, which extended from about 1300 to 1850. These periods of low solar activity, the Wolf, Spörer, Maunder, and Dalton minima, were times of extreme cold, frequent crop failures, famines, and human conflict. The impacts of the Little Ice Age on human cultures were large, even though the global decrease in temperature was only about 0.5 degrees Celsius. Okay, So solar activity from carbon-14 production. The record of changes in carbon-14 production serves as a proxy for solar activity. The production of carbon-14 decreases negative values when solar activity increases. All right, so over here we're looking at carbon-14 over time. You have the change in carbon-14 production on the y-axis, and then you have the years in the x-axis. Okay, this area right here represents the medieval warm period. Okay, and this area right here represents the Little Ice Age. Okay. You have the modern maximum here, the Dalton minimum, the Maunder minimum, the Sporer minimum, the Wolf minimum, the medieval maximum, and the Oort minimum right here. Okay, so this area right here shows that there is a strong correlation between solar activity and global temperatures, especially during the Little Ice Age. Okay, and over here, it shows that an increase in solar irradiance contributed to rising global temperatures in the first half of the 20th century. However, sunlight has been weakening for the past 60 years. All right, so you're going to use the equation for the area of a circle. Area equals pi r squared, and a sphere. Surface area equals 4 pi r squared to explain why the insolation or exposure to the sun's rays is at Earth's orbit, but is about 340 for any point on Earth's surface. So during the summer, the part of the world you're living in is warm because it is leaning towards the sun. Those experiencing winter live in the part of the world that is leaning away from the sun. When the Earth rotates, the sun lights up one side of the planet better than the other side, which is why the area of the Earth is more covered due to the exposure of the sun's rays. So for the area of a circle, we know that's pi r squared. Okay, so remember the area of the circle is the total number of square units that fits inside the circumference or the circle. Okay, so when the Earth spins on orbits around the sun, that's called revolution. One full orbit around the sun is one revolution, and it takes about 365 days to complete one revolution, which is why there is less surface area covered at any point on Earth's surface. All right, so for volcanic eruptions, cooling effects. So volcanic eruptions can increase global warming through the release of carbon dioxide, but they have more significant short-term cooling effects. Erupted sulfur dioxide reacts with water vapor in the atmosphere to form tiny droplets, aerosols of liquid sulfuric acid, H2SO4. These aerosols and volcanic ash block out sunlight and cause a cooling period that can last for years or much longer for large eruptions. Several historical periods of cold temperatures, agricultural failure, and famines correlate with large volcanic eruptions. So again, over here, you have the average surface temperature changes that are shown in this graph, with the y-axis being the temperature change in degrees Celsius and the x-axis representing the years. Okay. So in 1991, Mount Pinatubo erupts. Okay, so that's what's shown over here. So the Pinatubo temperature impact. Global temperatures dropped by more than a half a degree over the year following the eruption of Mount Pinatubo. All right, so now we're going to look at Mount Redoubt in Alaska. The eruption of Mount Redoubt in 2009 ejected vast volumes of volcanic rock, ash, and millions of tons of sulfur dioxide into the atmosphere. Erupted ash and sulfuric acid aerosols block out a portion of sunlight, yellow arrows, reflecting it back into space, causing a net cooling effect. All right, so now we're going to take a look at historic impacts. Okay, there have been many climate altering volcanic eruptions over the past 1,000 years. Okay, the effects of these eruptions have been quantified in records of ice cores and tree ring growth, as well as documented in historical records. The release of millions of tons of sulfate aerosols affects climates by altering atmospheric patterns, causing extreme weather events such as snow in the summer, flooding or droughts, as well as crop failures, famines, epidemics, and large-scale human migration. So again, this map right here shows the large eruptions being concentrated in this area right here. So most of the volcanic eruptions that altered global climates have occurred within the Ring of Fire, belt of subduction zones that borders much of the Pacific Ocean. So this area right around here is known as the Belt of Fire or the Ring of Fire. Okay. So there are some large volcanic eruptions that have taken place in that Ring of Fire. In 1257, in Rinjani Samalis, Lombok, Indonesia, the large volcanic eruption led to global cold temperatures, crop failures, and famines, helped trigger the start of the Little Ice Age. Okay, in 1452, a volcano in Kuwait Banatu, when this volcano erupted, it led to tree growth stunted globally, severe famines in China, Yellow River frozen for 20 kilometers out to sea, contributed to the second phase of the Little Ice Age. Okay, and then in 1600, in a volcano in Peru, when this volcano erupted, that led to severe cold and famines in northern hemisphere, particularly Russia, agricultural collapses in South America and Europe. Okay, and in 1783, a volcano in Laki, Iceland erupted, and that led to global freezing, droughts, and famines in Africa and southern Asia, severe weather and crop failures in Europe contributed to the French Revolution. Okay, in 1815, in a volcano in Indonesia erupted, which led to extreme cold and flooding in Europe, extreme cold and famines in eastern North America, driving the settling of western U.S. territories, extreme flooding in South Asia, triggering a global cholera pandemic. Oops. All right. So now we're going to examine the math of the Ring of Fire. and you're going to construct an explanation for why most large-scale volcanic eruptions occur in and around the area highlighted on the map. So guys, what did you guys say was the cause of volcanic eruptions in the Ring of Fire? Anyone? So does tectonic plates ring a bell? Yeah? So remember, Earth's surface is made up of a series of tectonic plates that slowly move into and apart from one another. Okay? The Ring of Fire is the result of these tectonic plates crashing into each other. The plates in the Pacific are moving faster than other plates around the world, adding stress where the plates interact. Okay, so again, these tectonic plates that are moving faster is what's causing the massive volcanic eruptions in the Ring of Fire. All right, so climate and humans, prehistoric impacts. Climate has impacted human history in many more ways than just volcanic eruptions. When climates were favorable, humans flourished and populations expanded. When climate shifted and became unfavorable, crops failed, populations diminished, civilizations collapsed, and conflicts between cultures increased. Okay? So trends in climate change have historically determined where agriculture could and could not be practiced, shaping the course of human civilizations. So this image right here is of the Persian Gulf 15,000 years ago. Okay, so over here, we see that the sea level rise and changes in coastlines are significant impacts of climate change on humans. Melting glaciers at the end of the last ice age caused sea levels to rise about 130 meters or 400 feet. So about 15,000 years ago, there was no Persian Gulf. Okay. Now fast forward to the present day. Okay. And now we see the Persian Gulf right along here. And we can see that as the sea level rose, the fertile deltas of the Tigris and Euphrates rivers were flooded and shorelines rapidly advanced inland. Okay. Early settlements had to be abandoned and are now under the Persian Gulf. Many early cultures share stories of expulsion from their homelands as a result of rising sea levels. Okay, so now we're going to go ahead and examine the two maps. The current shape of the Persian Gulf has changed little in the past 6,000 years. Okay. Um, We're going to calculate how fast the Persian Gulf coastline moved landward between 15,000 and 6,000 years ago. So we all know that distance is equal to rate times time, right? If we want to, but in this case, we want to go ahead and calculate the rates, right? So when we go ahead and arrange that, we get rate is equal to distance over time. Okay, the distance is 130 meters. Okay, as mentioned um, up here, this is where we're getting the 130 meters. And then it's over 15,000. Oh, you know what? It's supposed to be over 9,000 years because it's 15,000 minus 6,000. So it's 130 meters over 9,000 years. Okay? And then you're going to go ahead and solve that. And then you're going to go ahead and get your rate. Okay? So again, it should be 130 meters divided by 9,000 years. Thank you so much. You are so helpful. Okay, so accept. All right, does anybody have any questions about that? So just one more time. This is rate is equal to distance over time. So the distance is 130 meters. The time is 9,000 years. Okay, because 15,000 minus 6,000 is 9,000. Okay, so 130 meters over 9,000 years is going to give you 0.014 meters per year. Okay, so then you're going to take the 0.014 meters per year and multiply that by 9,000 years to get um, the distance.